Our final module in this short series is to look at decay rates, which are in some sense the opposite to the growth rates, but there is much in common. There is much regarding them that are similar. And one of the things we want to look at here as well is proportions, because again, we've talked about proportions all the time, and proportions are back here again, because the spreading of the disease and also impacts of vaccines have a lot to do with proportions. In other words, if you have, say, in a room, we'll say we often talk about particles or particles per million or something. If you have, say, 1 particle per million, it's probably not going to be a major threat. If you have 100,000 particles per million, then there is going to be a much greater intensity and density of the disease in the room. And so your chances of getting a disease is greatly impacted by the concentration of the virus that is in the air. Sometimes the word is used, and people in science will have probably a better way of looking at that. We call it ppm, parts per million, particles per million. As I said, looking at that, looking how it changes, clearly, as I said, if you're in an enclosed space, someone is breathing out, 20 particles per second, then over a minute, there's going to be 20 times 60. There's going to be 1,200 particles in the room. After another 10 minutes, there's going to be 12,000 particles in the room. So you can do the math of the various proportions and see and it comes back again to some of your probability. Your probability then of getting the disease is related to these parts per million as well. But what I want to look here at is more particles per million in some sense, and it's probably more in terms of particles per milliliter we would use, because we're looking at concentrations in blood. So what we're talking about here would be something such as, it could be any concentration of a drug in the body, but in particular here we can assume, we'll say that it's related to the vaccine. Now, the science people will tell you more about how much of the vaccine is in the blood and whatever, and I don't know that science, but we can just use some kind of hypothetical situation here. We'll say that the concentration, again, we'll use the numbers parts per million. So we'll suppose that you get a concentration of a drug, and we'll say it gives you, I'll use, say, just a fictitious sort of hypothetical number. We'll say 50 parts per million. And the 50 parts per million is going to have some effect on your system. It's either going to kill the symptoms, or it's going to kill the virus, or it's going to kill a bacteria, or it's going to do something anyway. So we'll say you are injected with 50 particles per million. And then we're trying to understand in some sense how long that will remain effective. So, as I said, your initial dose, 50 particles per million. Now, we'll say, just for the sake of argument, that we're trying to kill off some symptoms, kill off something that's causing you a distress, and we'll say this drug is effective until it is down to 5 parts per million. So if there is more than 5 parts per million in your bloodstream, it will be effective. What we often look at here then is the decay rate of this. In other words, what is it? How does this decay in the blood? And we often look at this in terms of what is called a half-life. Let us pretend again to keep life very simple here. We'll use, it's related to time again. So suppose that the half-life of this drug is 2 days. So that means after 2 days, the 50 parts per million have become 25 parts per million. Then after another 2 days, that's clearly down to 12.5. I'll write it as 12.5 for now. That means after another 2 days, it's down to 6.25. And then after another 2 days, it's down to 3.125. And remember we said that 5 parts per million were effective. So essentially the impact of the drug is gone at this stage. So if we're looking at it, so we'll suppose the drug is administered in day 1. So if that's day 1, then after 2 more days, it's that. After 5 days, it's that. After 7 days, it's that. That means after 9 days, it's that. So somewhere after about 7 to 8 days, the effect of the drug, because as I said earlier, the cutoff is the 5 ppm. Once you get beyond the 5 ppm, then it's no longer effective. So how would we model this? How could we come up with some kind of a formula? Well, this again is decaying in some sense at sort of but it's decaying at a slower rate. Essentially what we're doing each day is multiplying by 1/2. Sorry, not each day, but each time period. So it would appear to me so that the first time here, that would be 50 times 1. That would be 50 times 1/2. That would be half of that again, right? So it would appear to me that in this equation, in some place, in some sense, there is going to be multiplication by 1/2. After the first time period, it's multiplied by 1/2 to the power of 1, 1/2 to the power of 2. So we could really write it as 1/2 to the power of t, where t is the time period. But of course, if we did that, we would simply get 50. We just get 1/2, 1/4. So we have to multiply it by the 50. So if we have 50 times 1/2 to the power of t, then now if we say at the beginning, we're basically at time period 0. This would be essentially after 0 time periods. This would be at the end of 1 time period, the end of 2 time periods, the end of 3 time periods, the end of 4 time periods. And just to keep track of let me, we let that in blue as well to indicate that t is representing the same factor there, right? So in that case, if t is 1, that's 50 by 1/2. If t is 2, that's 50 by 1/4. If t is 3, that's 50 by 1/8. 50 by 1/16. And we can see these numbers are correct, right? So of course, what we would be looking at then in general, of course, is if we know that 5 is the magic cutoff, we could do all sorts of nice mathematics with this model. We know the model looks like this. Suppose now that we want, say, to have this drug be effective for, say, 10 weeks. Well, there would be a couple of ways of doing this. If we want it to be effective for 10 weeks, well, let's consider a little bit of mathematics. So we want this particular model to be effective for 10 weeks. That means in some way we have to adjust something, because if I just put a 10 in there for 10 weeks, I would simply get 50 divided by 1,000 or something. So it would be way, way too low. If we want it effective for 10 weeks, then we would have to adjust one of the others. We would either have to adjust the dose, that we have at the beginning to make it big enough. So I mean, let's look at that for a minute. I'll call 50 the dose. So what would I want to do there then? I would want to do something like, I would want to have some kind of a dose, and I would want to have this dose by 1/2 to the power of 10 be such that we are still greater than the effective cutoff. And remember, our effective cutoff is 5. So, I mean, that might be one possibility. In other words, I would want to solve that equation, the dose by 1/2 to the power of 10. I still want it to be greater than 5. And to solve that equation again means we'd want to understand our exponents. So essentially what we're doing there is we could multiply across, because that's really d by 2 to the power of -10. So essentially I would multiply the 5 by 2 to the power of 10. So my dose would have to be greater than 5 times 2 to the power of 10. Now, we have to be cautious then. Maybe that perhaps that dose is too large. In other words, 50 is the most we can safely introduce into the bloodstream. Then maybe what we could do is change another parameter. We could rewrite it in a different way. In other words, I can only introduce 50. So now I still want, at the end of 10 weeks, I want 50, this rate over 10 weeks, to still be greater than 5. So where does that let me? That means the variable that I can attempt to adjust perhaps this time is the decay rate. Perhaps instead of being 1/2, I will call it 1 over, I'll use D as a decay rate in some way, right? In other words, I would want a different decay rate. In other words, I wouldn't want it to decay as fast as 1/2, perhaps. And it might not be just 1 over D, it might be some other kind of fraction. So maybe let me actually write it as C over D. It's an actual fraction, because we'll want it to be bigger than 1/2. So then, of course, we have an equation here now to solve. And to solve that equation, we would divide across by the 50. So we would have C over D to the power of 10. Then we'd have to get the 10th root of 1/10. And so you can see here your need to be able to solve an equation with powers in it. And of course, to solve equations with powers in it means, and I'll just write this down very simply for a moment, just to show you something else that you might need to know and find to be useful and worth reviewing, because it is often the case when we are looking at exponents and growth rates, it's the inverse of it to solve, and that is the logarithm. So if I continued with this equation here, what that would really mean is I would want to rephrase it like this: C over D to the power of 1/10, and I'm going to divide across by 50. I want that to be greater than 1 over 10. And what I could then do is take the logarithm of both sides. So basically, if I take the logarithm of this side to be greater than the logarithm of this side, and then there's a rule with logarithms that I can bring down the exponent in front of the logarithm to get something like this. And I can take, say, natural logs, that 10 times the natural log of this fraction, or this rate. I could have probably just written it as, instead of writing it as a fraction, I could have just written the letter R as a rate. So 10 times the natural log of that must be greater than the natural log of 1 over 10. Of course, what that would mean is you could divide across then by the log again there. So basically you want 10 to be, you want the log of something to be greater than the log of 1/10 divided by 10. You could use your calculator or whatever to get the log of 1/10, the natural log of 1/10. And in that case, you could solve for the log of something. And then once you've solved that, you could get again the exponent to get back to solving for the rate. This is simply shown here to illustrate to you that once you get into power equations, you also need to get to have an understanding of logarithms. And we again suggest a website to you that you may look at logarithms, simply because there is this, the logarithms are important. You've done them in school and you didn't think they were, but they are very important in trying to solve equations because they are essentially the inverse of exponents. And in order to solve equations that involve exponents, you would need to understand logarithms also. And all of this kind of equations are important in the modeling of decay rates. They're important in the modeling of this type of phenomenon here, which would be related to decay in the bloodstream. And of course, we can come up with much more advanced models, but in a simple case, it shows again the type of mathematics, not extremely advanced mathematics, but mathematics that you need to understand aspects of the medicine that's treating these diseases. So I hope you will find time again to explore some of that, to try and see what's the best growth rate. Of course, you can see here where the scientists would be, of course, trying to continually devise drugs whose decay rates would be less, that you could use smaller doses with less side effects, so that with greatest impact. And the combination again of the scientist who can look at these mathematical models and use the mathematics before developing the science.